Unit 6A, Lesson 2. In this lesson, we're going to work with other types of probabilities. We're going to talk about the fundamental counting principle, factorials, permutations, combinations. There's going to be many new ideas and concepts in this lesson. First, we're going to discuss the fundamental counting principle, which we can use to determine the total number of possible outcomes when there are two or more different events occurring. So the fundamental counting principle states that if an event has m possible outcomes and another independent event has n possible outcomes, then to calculate the total number of possibilities or outcomes, we multiply m times n to get the total number of events or possibilities. Now we're going to go through an example to hopefully make sense of the fundamental counting principle. It's a pretty straightforward idea once you get the hang of it. Suppose you're going out to eat. You have 3 options to choose from for the main course, 3 options to choose from for a side, and 2 options to choose from for a drink. We want to determine how many different meal combinations could you create from those options. So our 3 main course options would be a chicken salad or turkey or grilled cheese. For each of those main courses, we have an option of 3 different sides, chips, french fries, or a fruit cup. And then for each of those, we have 2 options for a drink. We can get a soda or water. So we can see by creating this tree that the total number of possibilities we could create from those options is going to be 18 total combinations. We could quickly use the fundamental counting principle rather than creating this tree. So what we would do is we have 3 different options for our main course. So that's our first number of possibilities. There's 3. We're going to multiply that now by the number of options we have for a side, which is 3 different options. And then multiply that by the number of options we have for a drink, which is 2. So 3 times 3 is 9. 9 times 2 is 18 total outcomes. So that's how we can quickly use the fundamental counting principle to find the total number of outcomes, multiply the different outcomes from each of those different situations. Next, we're going to discuss factorials. In mathematics, the factorial of a non-negative integer n, denoted by n exclamation point, this notation means we're talking about a factorial, is the product of all the positive integers less than or equal to n. So for example, down below, if we have 5 factorial, that means we're taking 5 times every integer less than 5, every positive integer. So we're taking 5 times 4 times 3 times 2 times 1. So 5 factorial is equal to 120. Normally, you're going to see these numbers ordered from highest to lowest, so they would have 5 times 4 times 3 times 2 times 1. So for example, if we had 3 factorial, that means we're taking 3 times 2 times 1 to get a result of 6. 3 factorial is equal to 6. The basic notation for a factorial, n factorial is going to be equal to that integer n times the factorial of the integer 1 less than that number n. Now we're going to use those basic ideas of factorials to help us better understand the next couple of ideas, which are permutations and combinations. First, we're going to talk about permutations. So suppose we have n total objects, and we want to choose our number of objects out of that total, where the order in which we select them matters. Okay, that's referring to a permutation when the order matters. So this allows us to calculate how many different ways we can choose our objects out of a total of n where the order matters. We take n factorial, the total amount, divided by n minus r factorial. That is a permutation. A combination is very similar, except the order does not matter. So we have n total objects. We're going to choose our number of objects out of that total, where the order in which we select them doesn't matter. It's just which ones we have grouped or chosen. So that's n factorial divided by n minus r factorial times r factorial. So the only difference between a permutation and a combination is the order does not matter in a combination, and that affects our equation by having an extra r factorial in the denominator of the fraction in our equation. If you look at the table down below, we have a few different ways we can express the equation for a permutation and combination based on whether repetition is allowed. So the ones we went through, you could see this one for a permutation, which is the same as the one up above. That's probably what we're going to use most often. That is if repetition is not allowed. And the same thing for a combination. This is the same expression that we had up above. Repetition is not allowed. The two equations down below are if repetition is allowed. So for a permutation, if repetition is allowed, then the formula becomes n raised to the r power, so the total number of objects raised to how many we're choosing. For a combination, if repetition is allowed, then the formula becomes n plus r minus 1 factorial divided by r factorial times n minus 1 factorial. To end this lesson, we're going to go through a few different examples showing how permutations and combinations work. For the first one, suppose a class has 12 students and 3 need to be selected as volunteers for an activity. How many different groupings of students could there be? So the first thing we need to determine is whether or not this is a permutation or a combination. So we have 12 total students. We need to select 3 of those to be volunteers for an activity. It does not matter the order in which those 3 students are selected. All that matters for the different number of groupings is which 3 students we have grouped together. Okay, so it didn't matter if I chose Bob, Susie, and Riley, or if I chose Riley, Susie, then Bob. All that matters is it's 3 students that are grouped together, so this is going to be a combination. So for notation, we're going to use a C. In our parentheses, first we have 12 total objects, comma, and we're selecting 3 out of that total. Now putting this in our formula, our total objects goes in the numerator, so we would have 12 factorial divided by, in parentheses, we're taking our total minus the amount we're choosing, so we'd have 12 minus 3 factorial times 3 factorial, the amount we're choosing. So simplifying this a little bit, we have 12 factorial divided by 12 minus 3 is 9 factorial times 3 factorial. For the numerator, I can rewrite 12 factorial as 12 times 11 times 10 times 9 factorial. The reason I would do that is because now I have 9 factorial in the numerator and denominator that I can simplify out. So all I'm really doing is taking 12 times 11 times 10 and then dividing that by 6, because 3 factorial was 3 times 2 times 1. In the numerator, we get 1,320 divided by 6, which simplifies to 220. So if we had a class of 12 students and 3 needed to be selected as volunteers for an activity, this is a combination because the order does not matter. There would be 220 different combinations we could use to select those 3 volunteers. Now we're going to move on to the last example. Suppose a class of 15 students needs to select a class president, vice president, secretary, and treasurer. How many ways could they select these positions? This is different than the last problem because in the last problem we just needed 3 volunteers. We couldn't distinguish one volunteer from the other 2. We just needed 3 positions or 3 volunteers. This one is different because each of these 4 spots is different. We have a class president, a vice president, a secretary, and then the treasurer. They're distinguished from each other, so the order in which we select the student for a position does matter. That is why this problem is going to be a permutation. This time for notation, we use P, comma, we have 15 total objects, 15 students, comma, 4, we're selecting 4 students out of that 15. In the numerator, it's going to be 15 factorial, our total number of objects, divided by 15 minus 4 factorial. Just like the last problem, I can rewrite the numerator into 15 times 14 times 13 times 12 times 11 factorial, because now I can simplify my 11 factorial from the numerator and denominator. So to calculate this permutation, you're taking 15 times 14 times 13 times 12, which gets you 32,760 possibilities. So for a class of 15 students, the number of ways you could select a class president, vice president, secretary, and treasurer, because the order in which you select the students matters, there are 32,760 different possibilities or ways you could select those students. We went through a lot of information in this lesson. First, the fundamental accounting principle, which allows you to quickly calculate the total number of outcomes for independent events. You just multiply those possibilities together. Then we talked about permutations and combinations. The main thing to remember between the two is that for permutations, the order in which you select the objects matters. For combinations, the order does not matter.